Hello guys, this is 10.4. We're looking at comparison tests. In the last week we talked about direct comparison tests. Let's just do a quick review. All right, so let's I have two series like that. Let's say AN and BN. Okay. Actually, let's do AN here, BN. All right, so what the direct comparison test says, if the terms AN are smaller than terms BN, right? So AN is less than BN, then if AN diverges, means BN will diverge. On the other hand, if BN converges, then AN converges. Okay, so that's what the direct comparison test is saying, right? So if the larger one converge, then the smaller one will have to converge as well. If the smaller one diverge, then the larger one would diverge as well. And then we also talked about P series and geometric series, when they will converge and when they will diverge. Let's just do a quick review. All right, so P series, right, 1 over n to the P converges when P is greater than 1. Now, if you have a geometric series, which will look like 1 over, like some constant. I forgot which constant we used. That's R ratio, R to the power of n, right? Then a geometric series converges when R, the absolute value of R, is less than 1. Right, so you're taking a fraction like 1/2 to the many power, and then eventually it will converge. Right, so these two series, they are quite useful, P series and geometric series. Right, they are commonly used to study infinite series. All right, let's do one example with direct comparison test. All right, so consider this series, right? 1 over radical n plus 1 times 4 to the nth power. Let's call this AN. Now we're going to choose BN to be 1 over 4 to the n, since as n gets larger, 4n is much larger than square root of n plus 1, right? So the 4 to the n power outgrows square root of n plus 1 as n gets large. And we know that the infinite series of 1 over 4 to the n, which is our Bn, converges because it's a geometric series with r equal to 1 over 4, right? A geometric series converges when absolute value of r is less than 1. Therefore, we know that 1 over the original AN is less than 1 over 4 to the n for n greater than 1, right? Because we're taking away the square root of n plus 1. So we have less things in the denominator. That means the value is greater. Then we can say, since Bn, infinite series of Bn converges, the original An is going to converges by the direct comparison test, right? Because we have shown that the larger one converge, the larger converge, means the smaller one will converge. Right? So the larger one is our 1/4 to the power of n, which is a geometric series that converges. So the smaller one, which is our original An, will converge due to direct comparison test. Now, there are some cases where direct comparison test is actually inconclusive, and we have to choose a different test. And let's take a look at an example of that as well. All right, so let's take a look at this series, n over square root of n cubed plus 1. All right, so again, let's just call that An. And then we're going to introduce Bn, so choose Bn to be n over square root of n cubed, right? Now this plus 1 in the denominator here, it's not going to matter when n gets large, right? So we can drop that and simplify this thing. And that simplifies down to 1 over the square root of n, which is 1 over n to the power of 1/2. Now, this is a P series, right? Now, does it converge or diverge? So take a second to think about that. So P series, 1 over n to the power of P, will converge if P is greater than 1, right? So since P is equal to 1/2, which is less than 1, series diverges. Okay. But if we compare Bn with the original An, since we have the one less in the denominator, that means this is going to be greater, right? That's An, that's Bn. Bn is greater. Now, but here we have the larger series diverges. The larger one diverges. But direct comparison test only says that if the larger one converges, then the smaller one will converge. But here we have the larger one diverges. Therefore, the direct comparison test does not apply. Right? And we have to use another test. We must use another test. Okay, and this is when we are going to introduce our next comparison test, which is called the limit comparison test. Now, before we move on with the limit comparison test, let's do a quick review on limit test, right? Which is comparing the growth rate of f and g. Right? So let's say if limit as x approaches infinity of f over g is infinity, then we say that f grows faster. Right? Now, if you take the limit of f over g and it's equal to 0, then in that case, we say g grows faster. Right? And if you get some constant from the limit, then we say that f and g grow at the same rate. Okay, and the next comparison test is basically the limit test, right? Instead of functions, we are looking at series. Okay, series, not series, series. Okay, so let's take a look. All right, so the limit comparison test, given some series, an, infinite sum of an, and the known convergent or divergent series of Bn, right? So notice that Bn, we know that it's converging or diverging already. So most of the time, this will be like a P series or a geometric series, something we know a lot about. Okay, and there are three cases. First, when you take the limit as n approaches infinity of an over Cn, if it's equal to C, where C is a finite positive number, then the series will behave alike. They either both converge or both diverge. Just like the limit test, right? When you take the limit of the function and you get a constant, it means that both functions grow at the same rate, all right? So same thing here. If you take the limit of an over bn and it's equal to some constant c, then they are growing at the same rate, meaning they will both converge or diverge at the same time. Okay, next. Second one, if the limit is equal to 0, that means bn grows faster, right? That means bn grows faster. And if bn converges, then an is going to converge. So if the one that is growing faster will converge, then the one that's growing slower will also converge, right? So this is like what we're doing here, right? If the denominator grows faster than the numerator, right? And on the other hand, if the limit is equal to infinity, infinity means an grows faster and bn grows slower, right? So here bn is slower, right? And if the slower one diverges, then the faster one will diverge as well, right? So it's kind of like a direct comparison test, right? If you have something like this, right? Bn and an. Now, bn is going to converge. That means the slower one, an, will also converge, right? On the other hand, 4.3, if you have bn, which is slower, and an is faster, if the slower one diverge, then the faster one will also diverge. And we can show this by taking them in a rational form and take the limit as n approaches infinity, right? So it's a little different than direct comparison test. Direct comparison test, we're comparing them directly with each other. But here we're actually using the limit test idea and putting them in the form of rational expression and take the limit as n approaches infinity. All right, so let's take a look at one example together. All right, so let's take a look at this example that we looked at earlier, which is inconclusive based on direct comparison test. Now let's use limit comparison test. Let's see what we have. All right, so that's an and that's our bn. All right, so the idea is once you have your an and bn, go ahead and take the limit as n approaches infinity of an over bn. All right, and then we will have something like this. An, that's n over radical n cubed plus 1 divided by bn. So we need to flip that. That's radical n over 1. All right, so let's see what we have. Here I have limit n approaches infinity of n to the power of 3 over 2 over radical n cubed plus 1. All right, and what I'm going to do is I'm going to use the technique from Calc 1, which is multiply the top and bottom by 1 over n to the power of 3 over 2. Okay, and what will happen is that in the numerator, I'll just have a 1, right? Oh, so that's a 2. 3 over 2. Okay. So in the numerator, I'll have just a 1, and the denominator, I will have n cubed over n cubed plus 1 over n cubed, like that, right? And then that's equal to limit 1 over square root of 1 plus 1 over n to the third power, right? And when you take the limit as n approaches infinity, this term will go to 0. Right, this term will go to 0, leaving us just a 1. Right? Okay, so a 1 means an and bn, they grow at the same rate, means they both will behave the same way. So we can say since bn diverges, an will diverge. I should say an will behave like bn. So the infinite sum of an will diverges by the limit comparison test. Okay. All right. So when direct comparison test doesn't work, we can try limit comparison test, right? Put them in the form of an over bn, take the limit, and we're good to go. All right, let's try another one. All right, consider the series, infinite series of 1 plus 3n, 3 to the n, and over 4 plus 2 to the n. All right, so whenever you see like a plus 1 or adding a constant, they are eventually going to go away when n gets large, right? So in this case, we can choose bn to be ignoring the 1 and 4, so it will be 3n over 2n, which is 3 over 2 to the power of n. Okay, does this converge or diverge? Think about this. This is a geometric series. All right, with r equal to 3 over 2, which is greater than 1. So geometric series only converge when r absolute value of r is less than 1. All right, so it's greater than 1, so that means this is going to diverge. All right, so let's see. Let's see if this will diverge as well, right? Would the plus 1 and the 4 in the denominator make a difference? Let's check. All right, so take the limit as n approaches infinity of an over bn, which is limit 1 plus 3 to the n over 4 plus 2 to the n divided by bn. So flip that. That will be 2 to the n over 3 to the n. All right, and let's see what we have. Go ahead and do some distribution. All right, so I have 2 to the n plus multiply 3 to the n and 2 to the n, I get 6 to the n over 4 times 3 to the n plus 6 to the n. All right, and we're going to apply the similar technique, multiply the numerator and denominator by the reciprocal of the largest term. So in this case, the largest term will be 6 to the n because that's the one that grows the fastest. All right, something like that. All right, and let's see what we have. All right, of course, we are going to distribute that. Okay, so first, that will be 1 over 3 to the n plus 1 over 4 times, that's 1 over 2 to the n plus 1 over 6 to the n. All right, so when n goes to infinity, oh, sorry, that's 1. All right, 6 to the n, multiply 1 over 6 to the n, that's a 1. All right, so when n approaches infinity, right, the 1 over 3n, that's going to go to 0. Right, that's going to go to 0. And this 4 times 1 over 2 to the n, as n gets large, that's also going to go to 0. All right, leaving us just 1 over 1, which is 1. All right, that means an and bn behave the same way. So when we get 1, means an and bn behaves the same. Therefore, we know Bn diverges because it's a geometric series with r equal to 3/2, which is greater than 1. So we can say that. Therefore, the original an, which is 1 plus 1 plus what? 3 to the n. Over 4 plus 2 to the n diverges by the limit comparison test. Okay. All right. So our last example, actually, if you guys want, I really suggest you guys to pause the video right here and try to see if you can use the limit comparison test on this infinite series and to see whether it converges or diverges. Okay. Now, let's go ahead and do this. So that's our an. Right. Now, remember that we talked about like the adding constants, they're not going to do so much when n gets large, right? So we're going to choose our bn to be ignoring the +1, 4 and the +1. So it'd be and the 3 and the 2, right? That's not gonna matter too much. So we'll have n over n to the third power, which is 1 over n squared. So does this converge or diverge? All right. That is a p series with p equal to 2. So when does a p series converge? Right? When p is greater than 1, right? So this actually converges. All right. So we know that bn is going to converge. Let's compare that with an. Limit as n approaches infinity of an over bn. Um, 3n plus 4 over 2n plus 1 to the third power. That's an, and divided by bn, which is just n squared over 1. All right, and same thing. Let's go ahead and multiply everything in. All right, limit and approaches infinity. So 3n cubed plus 4n squared over 2n plus 1 to the third power. All right, to the third power. So notice that this is a degree 3 polynomial, and the denominator, it's also a degree 3 polynomial, right? And from our Calc 1, we know that if you're taking the limit to infinity and you have the same degree in both the numerator and denominator, then the limit is actually just the ratio of the leading coefficient. So actually, let me do one more step. All right, 3n cubed plus 4n squared over, and I'm going to expand the denominator. Now you can expand the denominator, multiply now or whatever, but all I care about is the first term, right? I know it's an to the third power. Actually, I know the rest. Second one is going to be 6n squared plus 6n plus 1. Is that right? 1, 3, 3. Oh, no. This is going to be 3, 12n squared plus 6n plus 1. Yeah. Anyway, we don't care about these three terms. Don't care. Right? Because when we take the limit, the leading term, the term with n cubed, that's going to outgrow the rest of them, right? So this will outgrow, this will outgrow these. Okay, same thing here, right? This term will outgrow the 4m squared, right? So when we take the limit, that's just going to go to 3/8, right? The quotient of the leading coefficient, 3 over a. So that's a constant, means an, bn behaves the same. All right. Now, since bn is a p-series, a converging p-series, let's write it out. Since bn is a converging p-series, oh my gosh, p-series, an will converge by the limit comparison test. Okay. All right. So, very fun limit comparison test is one of the things I really like to teach in Calc 2. Right. It shows us many different ideas that we learned from earlier with functions that can be integrated into learning about series and stuff. And series is a really big part of Calc 2 because later on in the chapters we will learn about different types of series, how we can use a series to represent a function. Okay, how to use an infinite series to represent a function. All right, so that's it for 10.4 comparison test, and I'll see you guys next time. Thank you very much.